Imagine standing in front of a skyline where glass, steel, and concrete are almost invisible. Instead, entire skyscrapers appear wrapped in trees. Balconies overflow with shrubs. Rooftops resemble small forests. From a distance, the city looks less like an urban center and more like a vertical jungle. This is not concept art. This is a real experiment. China is constructing residential towers designed to hold millions of living plants directly on their facades. Apartment buildings that function not only as housing, but as ecosystems. Structures meant to absorb pollution, produce oxygen, and cool the surrounding air. The idea sounds like science fiction, but in several Chinese cities, forests are no longer confined to parks. They are climbing into the sky, and China is betting that these vertical forest buildings could become a new model for the future of urban living. China's push toward vertical forests begins with a problem measured not in theories, but in human lungs. Over the past 4 decades, China has experienced the largest urbanization wave in human history. Hundreds of millions of people moved from rural areas into cities. Entire megacities appeared in a single generation. This rapid growth powered economic expansion, but it also produced extreme environmental pressure. Air pollution remains one of China's most persistent urban challenges. In many major cities, fine particulate matter known as PM 2.5 regularly exceeds World Health Organization safety limits. These microscopic particles penetrate deep into the lungs and bloodstream, increasing the risk of heart disease, stroke, and respiratory illness. Smog events can blanket entire metropolitan regions, reducing visibility to a few hundred meters. On severe days, schools close, flights are delayed, and residents are advised to stay indoors. China's cities also suffer from intense urban heat island effects. Dense clusters of concrete, asphalt, and glass absorb heat during the day and release it slowly at night, pushing temperatures several degrees higher than surrounding rural areas. During summer heat waves, this can turn city centers into dangerous thermal zones, increasing electricity demand and straining power grids. Green space per resident in many Chinese cities remains relatively low compared to urban populations. Traditional ground-level parks compete with housing, roads, and commercial development for limited land. In dense downtown districts, large new parks are often physically impossible to build. Planting more trees at street level helps, but it is not enough. China's vertical forest concept emerges from this reality. If cities cannot expand horizontally to add nature, they must integrate nature directly into the buildings themselves. Instead of separating architecture and ecology, the experiment attempts to merge them. Buildings become landscapes, and walls become forests. The concept of covering buildings with trees did not originate in China. It began in Europe. In 2014, Italian architect Stefano Borri completed a pair of residential towers in Milan known as the Bosco Verticale, or vertical forest. The towers featured more than 900 trees and thousands of shrubs and plants growing directly from balconies and terraces. Unlike decorative green walls, these were full-size trees rooted in deep planters designed to grow for decades. The buildings quickly attracted global attention. Studies estimated that the vegetation helped absorb carbon dioxide, trap dust particles, reduce noise, and lower surrounding air temperatures. The towers demonstrated that dense urban housing and large-scale greenery did not have to be mutually exclusive. Chinese urban planners saw something more than a striking architectural statement. They saw a scalable solution. China's construction capacity, centralized planning system, and willingness to test experimental urban models made it one of the few countries capable of attempting vertical forests at city scale rather than building scale. Instead of adding trees after buildings were finished, Chinese designers began exploring how entire residential districts could be conceived from the beginning as vertical ecosystems, where vegetation, irrigation, structural engineering, and maintenance systems were integrated into the architecture itself. The idea was no longer to create green buildings. The idea was to create living buildings. China's most ambitious vertical forest experiment is located in Liuzhou, a city in the southern Guangxi region. The project, often referred to as Liuzhou Forest City, was unveiled as a master-planned urban district containing residential towers, offices, schools, hospitals, hotels, and commercial buildings, all covered with vegetation. According to official project descriptions, The city was designed to incorporate more than 1 million plants and approximately 40,000 trees across its buildings. The vegetation includes hundreds of plant species selected for their ability to survive in local climate conditions and absorb pollutants. Planners claim that once fully operational, the district could absorb thousands of tons of carbon dioxide per year and produce hundreds of tons of oxygen annually. The buildings were intended to function as giant biological filters layered throughout the city. Luzhou Forest City was envisioned to house tens of thousands of residents, connected by electric public transportation and supported by renewable energy sources. In images released to the public, the city appears almost surreal. Towers emerging from dense greenery, with roads and walkways winding between what looks like a man-made forest. For China, Liuzhou represented a test case. If vertical forests could work at neighborhood scale, they could theoretically be replicated across dozens of rapidly growing cities. The project was not just architectural, it was a prototype for an entirely new urban typology. A vertical forest skyscraper is far more complex than a conventional high-rise with decorative plants. Every balcony, terrace, and rooftop must be engineered to support the weight of soil, mature trees, and water. A single large tree can weigh several hundred kilograms, and when combined with wet soil and planters, the load becomes substantial. Structural engineers reinforce floor slabs, columns, and cantilevered balconies to handle these additional stresses safely over decades. The buildings use integrated irrigation systems that automatically deliver water and nutrients to thousands of individual planters. Sensors monitor soil moisture, temperature, and plant health, adjusting watering schedules in response to weather conditions. Much of the irrigation water is intended to come from recycled gray water or captured rainwater. Plant species are carefully selected based on root behavior, wind resistance, sunlight tolerance, and seasonal patterns. Fast-growing species that shed excessively or develop aggressive roots are avoided. Many plants are chosen for their ability to trap particulate pollution and tolerate urban air. Maintenance is a continuous operation. Specialized crews use suspended platforms, climbing equipment, or rooftop cranes to prune trees, replace unhealthy plants, and inspect anchoring systems. In some experimental buildings, robotic devices and automated maintenance rails have been tested to reduce long-term labor costs. Fire safety systems are also adapted. Vegetation zones are compartmentalized, irrigation doubles as a fire suppression aid, and non-combustible planter materials are used to reduce risk. In effect, each building operates like a vertical park supported by a high-rise skeleton. Architecture and horticulture become inseparable. The primary promise of vertical forest buildings is improved air quality. Leaves capture airborne particles such as PM2.5 and PM10, reducing the amount of pollution circulating at street level. Plants also absorb carbon dioxide and release oxygen through photosynthesis. While a single building cannot clean an entire city's air, large clusters of vegetated towers were expected to create localized improvement zones. Another goal is temperature control. Vegetation shades building surfaces, reducing direct solar heating. Through evapotranspiration, plants release moisture into the air, producing a natural cooling effect. This can lower surrounding temperatures by several degrees, easing demand for air conditioning and reducing electricity consumption during heat waves. Vertical forests are also designed to reduce noise pollution. Leaves and soil absorb and scatter sound waves, softening traffic and construction noise around residential areas. Beyond environmental metrics, planners hope to improve quality of life. Residents would live surrounded by greenery rather than concrete. Windows would face leaves instead of neighboring walls. Access to nature, even in high-density housing, is associated with lower stress, improved mental health, and better overall well-being. In theory, vertical forests offered a rare combination: high-density housing, environmental remediation, and daily contact with nature, all within the same structure. As vertical forest buildings move from renderings to reality, serious challenges emerge. Maintenance costs prove far higher than expected. Thousands of plants per building require constant care. If irrigation systems fail or maintenance slows, vegetation quickly deteriorates. In some early projects, residents reported insects attracted by dense greenery, including mosquitoes and ants. Humidity levels increased near vegetated facades, raising concerns about mold and moisture damage. Not all residents were comfortable living behind thick layers of foliage. Blocked views, falling leaves, and reduced sunlight made some apartments less desirable. Most importantly, large-scale air quality improvements were difficult to measure. While plants clearly benefit immediate surroundings, they cannot offset the emissions of millions of vehicles and factories. Vertical forests work best as architectural features, not as standalone pollution solutions. China has not abandoned the vertical forest idea, but it has adjusted expectations. Some large projects, including parts of Liuzhou Forest City, experienced slow occupancy and redesigns. Developers began scaling back the amount of vegetation per building, focusing on selective green facades, rooftop gardens, and hybrid designs rather than full-coverage forests. Newer projects combine vertical greenery with traditional parks, green roofs, and urban tree corridors instead of relying on towers alone. The experiment continues, but in a more cautious form.